So welcome to Robotics 1. In this class, we are going to talk about mainly articulated robot, which means we'll talk about the robot arms. So we will look at robot arms. Robot arms are used in lot of applications. They could be used for pick and place. They could be used for painting. They could be used for automotive handling application. They can be used for automation line, pharmaceutical lines, and so on and so forth. A typical robot arm would look something like this. So you would have a base, then you are going to have link number 1. You are going to have link number 2. You can have multiple links, and at the end, maybe you have a claw. So this end part is called as the end effector. And where this is called as the link. And two links are connected by a joint. So what you have here is a joint. In robotics, what you can do is, if you have a very complex robot, that robot can finally build using some links and some joints. So there are two important things. What you have is you have a rotary joint. Rotary joint. So rotary joint, think about it, it's like a hinge. It is called as R. And you can have a prismatic joint. It is called like a cylinder. So if you look at a rotary joint, it's going to be something like a hinge. And you have a prismatic joint that would be something like a cylinder. So as you can see, rotary joint, degree of freedom, or the way the rotary joint moves, it moves in the angular direction, and reciprocating or prismatic joint moves in the linear direction. Now, whenever you have a robot can be constructed by a bunch of rotary joint and prismatic joints. So what I will do is I will bring a physical robot, and then we can identify what are the different ways, what are the different joints that you observe in the robot. So when we take a tour of the robotics lab at the end of the class, we will show you the different types of robots that we have, and then we can identify what type of structure these robots have. There are different configurations of robot. You can have a delta robot. You can have a Skira robot. But at the end of the day, each robot can be represented as combinations of links and joints. So you would have multiple links and joints. For an example, if you look at our arm, if you have a robot arm, you can have a rotary joint, you can have a reciprocating joint. The important thing here is, how do we find out where the robot is based on the joint angles? So imagine that you have a robot. So for example, I'm showing you, I have this robot. This robot joint is θ1. This robot joint is θ2. And what you have is, you have a position of the end effector. Now, I want to know as a roboticist, where is the end effector with respect to my 0, 0. So if this is my 0, 0, if this is my world frame, this is my fixed coordinate, I want to know where is the end effector. So forward kinematics is given the joint angles, find position of end effector. So first we are going to study what the forward kinematics is. There is also inverse kinematics, which is given the end effector position find joint angles. Now, for the sake of simplicity, let's consider a very simple robot. So what you have is, you have this robot, and this is kind of a one-link robot. Please note that this one-link robot has this joint. This is a revolute joint. So I'm calling this R. Then what I have here is I have a link L. And this joint is making this angle theta. And since this is the end effector, EE stands for end effector, I want to find out the position of end effector with respect to the inertial frame or the reference frame. What do I mean by inertial frame? Inertial means not moving, fixed, grounded. So I'm going to set up a coordinate system here. I'm going to say this is my y coordinate. I'm going to say this is my x coordinate. And I want to find out where that end effector is with respect to this origin O. Or in other words, this is going to be my 0, 0. All of you know the Pythagorean theorem. You know sine and cosine. So what I can do is, I can draw a vertical line down. I can draw a horizontal line. And this distance is L cosine theta. And this distance is L sine theta. And I'm going to call this point P. So I can say XP, which is the horizontal position, is L cosine theta, and YP, which is the vertical position, is L sine theta. Please note, L is fixed. Do you agree with me? L is fixed. The only thing that changes is theta. So imagine if you have a motor here, and that motor would move the link from position 0 to 35 degrees, 45 degrees, all the way to 90 degrees. So I can substitute the value of theta and get the value of XP and YP. So I can substitute value of theta. So theta is known, and find XP, YP. This problem is forward kinematics. Do you agree with me? Given the joint angles, finding out XP and YP is the forward kinematics problem. Now, in some cases, I give you values of XP and YP and ask you what should be the theta to get those XP and YP. So I give you values of XP. So now here XP and YP is given to you and you have to find out value of theta. This is called as the inverse kinematics. For a simple 1 degree of freedom robot, this is actually a planar robot. This is not a very difficult problem. You can solve it very easily. But imagine a case where you have 6 links, 6 joints. This problem becomes quite complicated. And usually we solve these inverse kinematics problem using some type of software simulation software such as MATLAB or Python. Please understand, it is extremely important to know forward kinematics always has a solution. Forward kinematics always has a solution. Inverse kinematics may have a solution, may not have a solution, or may have multiple solutions. So I need to write this down. Forward kinematics, always solution. Inverse kinematics may be solution, may be one solution, may be multiple solutions, or maybe no solution. And I give you a very simple example of no solution. If I give you XP and YP here, XP and YP here, do you agree with me? No matter what the value of theta is, that XP, YP position, since it is outside the workspace of the robot, cannot be reached, which means there is no solution. Everyone understood this? So a robot, inverse kinematics, may have one solution, could have multiple solutions, could have no solutions. Let me give you the example of multiple solutions. For an example, if you have a 2-link robot and we are trying to find out, so I give you this XP and YP. I give you this XP and YP. You agree with me that this position can be achieved using our elbow up configuration. It can also be achieved elbow down configuration, which means you can achieve the same end effector position different ways. So clearly, in this particular case, you have multiple solutions. So you can have different values of theta, and you can have a pair of theta 1, theta 2. You can have another pair of theta 1, theta 2. So here is an example where you have multiple solutions possible. Yeah.
Is any one solution has to be at the edge of the work envelope?
So one position could be, so usually at the end of the work envelope, what you have is you have singularity in all the joints aligned. So at the end, so to answer your question, yes, it's when you construct the work envelope at the boundary of the work envelope, what you have is you have one solution. But sometimes the work envelope may not be complete. What it means is you can have a spherical work envelope, but because of the physical geometry of the robot, some parts inside that work envelope cannot be reached. So for example, I have the robot, but that robot cannot go all the way over here because there is a hardware here, there is a link here that's going to obstruct. So there are regions in the work envelope that robot cannot physically reach. There are some regions where they are on the edge of the work envelope. And when they are on the edge of the work envelope, the problem becomes is the robot is fully extended, and then sometimes the robot encounters singularities. It means it gets into something called as lock position. And we'll talk about all this. But before I go further, any questions on the forward kinematics, inverse kinematics, rotary joint, prismatic joint? If I give you a one link robot, if I ask you to find the forward kinematics, solve the forward kinematics, given the L, given the theta, you will find XP, YP. If I ask you to solve inverse kinematics, then if I give you XP and YP, you will try to find the value of theta. Everyone understood this? So the questions on this section could be rotary joint, prismatic joint. I will show you a physical robot, and then you have to identify the rotary joints, prismatic joints, and sometimes what you need to do is you have to construct something called as the kinematic diagram, which means the robot is this physical robot, but to solve this robot mathematically, we have to come up with a simplified representation of the robot. And that is called as the kinematic diagram. So when we are going to perform forward kinematics or inverse kinematics, we will use this kinematic diagram to perform these calculations. Now, one important thing is whenever we are solving the kinematics problem. What is kinematics? Kinematics is nothing but study of displacement, velocities, acceleration. We don't include any forces. So if we were to include forces, that becomes a dynamics problem. Kinematics only deals with motion. So when we analyze robot, we deal with different types of frames. Now, why is this frame problem important? Now, before I give you the frame equations and then before we derive it, I want you to understand that if you look at the robot that I have drawn on the top, you have a link and you have a reference frame. This reference frame, assume this reference frame is fixed. This fixed reference frame is called inertial reference frame. So this reference frame is called inertial or fixed reference frame. However, please understand that link shown by L is rotating. So to analyze that link, we may have to assume a reference frame that is attached to the link. So we may have to assume a reference link that is attached, reference frame that is attached to this link. So assume that this is link number 2. This is link number L, and here is this reference frame. Now, please notice, since that magenta reference frame is attached to the link, as the link is rotating, that reference frame is going to rotate. You agree with me? So you have one red reference frame which is fixed. and you have another reference frame which is moving. So I need to find out what is the relationship between the fixed reference frame and the moving reference frame. And that is called as rotation transformation. It is extremely important in robotics. Now imagine you can have one more link. Then on that link, there is going to be another reference frame. So understand, as your links keep on increasing, number of reference frames keep on increasing. So you need to track all that. So you need to see how these reference frames are moving with respect to each other. Now, one thing that I want you to keep in mind that in all engineering classes, we use right-hand coordinate system. What is the right-hand coordinate system? The right-hand coordinate system means you have three fingers, and now your thumb is pointing in X direction. First finger is pointing in Y direction, and Z is coming out of the board. Everyone understood this? So X, Y, Z. The next thing that you should keep in mind is the rotations. The rotation is positive if you curl your right hand in the direction of rotation, and if your thumb is pointing in the positive direction, positive X, positive Y, or positive Z, that rotation is positive. And I'm going to write this down. So we are always going to use right hand coordinate system. So this is right hand and coordinate system. And I'm gonna write here, this is your positive X axis. This is your positive Y axis. This is your positive Z axis. Now imagine if I have a rotation like this. Curl your fingers in the direction of rotation, right hand. Curl your fingers in the direction of rotation. Your thumb is pointing towards positive X axis. So this rotation is positive. If I give you rotation like this, and why is this important? Because all the robots are three-dimensional structures. We are not gonna do any two-dimensional stuff here. Everything will be 3D. Curl your fingers in the direction of rotation, and can you see your thumb is pointing in positive Y direction? So this rotation is positive. Same thing with Z. Curl your fingers in the direction of rotation, and your thumb is pointing in the positive Z direction. So that rotation is positive. Everyone understood this? So always right hand coordinate system. Anytime if you have any questions, remember X is thumb, Y is first finger, and the middle finger gives you the direction of Z. So if you have X towards right, Y going up, your Z is going inside the board. Everyone understood this? Always remember, this is X, Y, Z. Because when you use the graph paper, horizontal axis is X, vertical axis is Y, and Z is coming out. Everyone understood this positive configuration, right hand thumb rule is called as right hand thumb rule. Now, let me give you a very important derivation. And this question may be on today's quiz in some other shape or form. So please pay attention. So I'm gonna talk about this X and Y axis. You have this X axis and you have this Y axis. I'm gonna call this XO and YO. So these are, and you agree with me, my Z is coming out of the board. Do you agree with me? X, Y, Z is coming out of the board. Now assume that this axis is fixed. And then I have another set of axes, which I'm gonna call X1 and Y1. So X1 and Y1. So this is X1 and Y1. Now please note, XO and YO, these are the old axis, old or reference axis. And X1 and Y1, these are the new or rotated axis. Now this angle, I'm going to call this angle as theta. And you agree with me, if this angle is theta, this angle will also be theta. You agree with me? Since XO and YO are perpendicular, so you have these two that are perpendicular, these two are perpendicular. Now what I want to do is, I want to find out the relationship between XO, YO and X1, Y1. I want to find out the relationship between XO, YO and X1, Y1. So what I do is, I drop vertical lines. So I drop perpendicular. And these vectors are unit vectors, which means the magnitude of vector is 1. So this is a unit vector. Unit vector. Which means the magnitude is equal to 1. So if the magnitude is 1, can you see that from Pythagorean theorem, this is going to be cosine of theta. Do you agree with me? This is going to be cosine of theta. Then you notice that here, this is going to be sine of theta. Then you observe this would be sine of theta, and you agree with me, this guy would be cosine of theta. And I will repeat this once again. Now let's understand. The old frame is X naught, Y naught. The old frame is not moving. Old frame is fixed, denoted by these dashed lines. But the new frame that was initially aligned with the old frame rotated by angle theta. So initially, when theta was 0, x1 and x0, they were aligned. Y1 and Y0 were aligned. As theta changed, then the x1 and y1 started rotating. Now, what I want to do is, I want to find out the relationship between these two coordinate frames. What is the relationship between these two coordinate frames? So it is not difficult to see that this is cosine theta, this is sine theta. So, but please understand, the projection of x1 on x0 is cosine theta. Projection of y1 on x0 is minus sine theta, because please note, you are going in this direction. Projection of y1 onto y1 into y0 is cosine theta. and projection of x1 onto y naught is sine theta. Now I want you to understand. I will give you a minute to look at this arrow. Once again, I want you to focus x naught line. Look at focus x naught line. I want to resolve the new coordinate frame onto old coordinate frame. What do I mean by resolving? Resolving means find the component of x1, find the component of y1 which lies on x0. Find the component of x1, find the component of y1 that lies on this line x0. So if you look at x1 cosine theta, can you see the direction of the arrow is in the same direction as positive x0. But when I look at the projection of y1 onto x0, can you see that this guy is not in the positive direction? So projection of y1 onto x0 is in negative direction. Everyone understood this? Now same thing. I want to find out projection of x1 onto y0. Projection of x1 into y0, can you see this is in vertical direction? Sine theta. Now projection of y1 onto y0, can you see this is cosine theta in the same direction? Everyone understood this? So what I'm trying to say here is, and I'm going to write this down. To resolve x1, y1 on x0, y0, we have to find appropriate sine and cosine component. So check this out. x0 is equal to, I can say x1 cosine theta minus y1 sine theta. y0 is equal to x1 sine theta and plus y1 cosine theta. Do you agree with me? There will be a quiz question, so make sure you understand this. Any questions here? Now notice z-axis is over here. So z1 and z0, they are already aligned. Can you see z1 and z0 are already aligned? Because z1 is coming off the board and z0 is also coming off the board. You agree with me? So this is x0, y0, z0. x1, y1, z1. z0 and z1, they are aligned. That's why there is no rotation. Everyone understood this? This is called as the rotation transformation. Extremely important. And this transformation will be used in all the problems we solve in robotics 1. So I'm going to ask you to look at that figure and make sure that everyone understands how we have taken the projections, how we have taken these signs. We are trying to find out the relationship between the fixed frame and the moving frame or the rotating frame. Both these frames are at the same point, but the first frame, x0, y0, is fixed. x1, y1 is rotated by theta. And I want to find out what is the relationship of the new frame to the old frame. What is the relationship of the new frame to the old frame? Now this is a simple algebraic equation. I want to write this equation in a matrix form. And the matrix that I'm gonna get is called as the rotational matrix. The matrix that I would get is called as the rotation matrix. We would solve all forward kinematics problems using the rotation matrix.
Wait, so when you say like x is equal to x1 will be like what? That's the interceptor?
Right, one.
Okay.
But in this figure, for explanation, I showed x1 and y1. So think about it. This guy is x1. Projection of x1 onto x0 is x1 cosine theta. Projection of y1 onto x0 is y1 sine theta. In the negative direction. Projection of x1 onto y0 is x1 sine theta. Projection of y1 onto y0 is y1 cosine theta. I'm just writing this for the reference because now I want to express these equations in a matrix form. How do I write these equations in matrix form? So I'm going to have x0, y0, z0 over here. Then I'm going to have a 3 by 3 matrix. And this 3 by 3 matrix will be multiplied by x1, y1, z1. So let's start with the easiest part. Can you see z0 is equal to z1? So I can say x1 is multiplied by 0, y1 is multiplied by 0. So my third row is going to look like 0, 0, 1. Everyone is comfortable with matrix multiplications? So when I multiply this row 0, 0, 0, 0 times x1 plus 0 times y1 plus z1 times 1 gives me z0 is equal to z1. You agree with me? Same thing, I have to do it for the first equation. And can someone tell me what would be my first equation? Cosine theta minus sine theta 0 sine theta cosine theta 0. So which means when I multiply cosine theta x1 minus sine theta y1 0 times z1 sine theta x1 cosine theta y1 0 z1. So I get the same set of algebraic equations. You agree with me? Now, what I'm going to show you is I'm going to show you a simple trick to derive the rotation matrix. But this rotation matrix is the rotation about z. Why this is the rotation about z? Because z0 is equal to z1. This is the rotation about z. This rotation matrix is called the rotation matrix about z. Similarly, you can have rotation about x. You can have rotation about y. And please understand, in that case, you will form those rotation matrices using the same technique that I showed you. And in the quiz, I may give you a question like find the rotation matrix about x. Find the rotation matrix about y. Or you have sequence of rotations. The first rotation is about x, second rotation is about y, third rotation about z. So you may, so before I'm spending so much time on these rotation matrices, because these should be absolutely clear. This is the fundamental building block of forward kinematics. Any question on this rotation matrix? Everyone understood? If I ask you to derive the rotation matrix, you will be able to derive. Now I will tell you a short trick. Now, so the simple trick is, if you want to derive rotation matrix, always look at the projections. So you are going to have the new frame here, and you are going to have the old frame over here. What do I mean by new frame and old frame? So for an example, in this problem, you are going from 0th frame to the first frame, x0, y0, z0, and you are going to x1, y1, z1. So x0, y0, and z0 is your old frame. x1, y1, z1 is your new frame. Everyone understood this? If you are going to the third frame, maybe x3, y3, z3, in that case, x2, y2, z2 will be your old frame. x3, y3, z3 will be your new frame. So let me write this down here. So the old frame is x0, y0, z0. The new frame is x1, y1, z1. And remember this, you will do projection of and projection on. And this will be clear in just 1 second. So I want you to look at the figure. Okay, don't look at the rotation matrix that I have derived. Look at the figure and tell me what is the projection of x1 onto x0. What is the projection of x1 onto x0? Cosine theta. What is the projection of y1 onto x0? Y1 onto x0? Negative sine theta. What is the projection of v1 onto x0? 0, because they are orthogonal. They can't have projection. If you have two vectors which are perpendicular to each other, which means this vector cannot affect this vector. This vector cannot affect this vector. Everyone understood? That's why these vectors are perpendicular. If you take linear algebra, you will look at the orthogonal rows and orthogonal columns. It means those are orthogonal to each other, perpendicular to each other. Their dot product is 0. So z1 is 0. Now same question. What is the projection of x1 onto y0? Projection of x1 onto y0. Look at the figure. Sine theta. What is the projection of y1 onto y0? Y1 onto y0. Cosine theta. What is the projection of z1 onto y0? 0. What is the projection of x1 onto z0? x1 onto z0. No relationship between x1 and z0. 0. y1 onto z0. 0. z1 onto z0. 1. So can you see that you got the same rotation matrix that we derived from the vector algebra or matrix algebra? Any question? Once again, when we start solving forward kinematics problem, this rotation matrix which is the rotation about z, will always come, and you should remember this. Cosine theta minus sine theta, cosine theta. That is going to be the rotation matrix. Since z1 and z0 are aligned, there will be 1 here, and all other elements will be 0. So cosine theta minus sine theta, cosine theta is the rotation matrix that you will use all the time. Everyone understood this?
Or just see about this.
We'll always assume our rotation is about z. This is the only rotation matrix that you should remember. Anyone studied robotics before coming here? Yeah. Then we talk about multiple rotation matrices. No. In robotics 1, the only rotation matrix that we should be remembering is the rotation about z. I may ask you to derive the rotation matrices about x and y. But as far as forward kinematics is concerned, for all the robots, we should only be looking at the rotation matrix. Wow. Everyone understood this? Any question? Okay. So we are ready to solve forward kinematics problem. Now, today I will solve forward kinematics problems by hand. But in next class, I will show you how to solve forward kinematics problem by MATLAB and also how to solve the inverse kinematics problem. So in today's class, I'm gonna do matrix multiplication by hand. So please be careful. Make sure that I'm not making mistakes, and then take down all the notes, because today's quiz you will be doing multiplication, matrix multiplication by hand. It's painful, but that's what we will be doing in today's lesson. Okay, so I'm gonna start. So check this out. So let me draw a robot. First, let me draw a robot. So what I have is I have a robot wherein you have this motor, and then there is this link number 1. There is this link number 1. And then on this link, there is another motor. And then here, there is link number 2. So what you have, and I'm drawing this robot like this because I want you to note that this is a 3-dimensional robot. This is not a 2-dimensional robot. And this is the end effector of the robot. This is the end effector of the robot. Now, this robot may look different. I mean, robot could be hanging upside down, robot could be mounted on the wall, or robot could be mounted on the ground. No matter how the robot configuration is, we have to come up with a simplified representation. And that is called as the kinematic diagram. So this is, think about this, this is like a physical robot. This is a physical robot. And step number 1 is to come up with a kinematic configuration, a diagram which can be used to work out forward and inverse kinematics. Everyone understood how this robot is? This robot has one motor here. This robot has one motor here. And you have link number 1, you have L1 here, and you have L2 over here. So this is how this robot is. So there are 2 links. And what I'm going to do is, I'm gonna give you dimensions of the robot. So the dimension of the robot is this robot, center line to center line. This distance is A1. This distance, center line to center line. This distance is A2. This distance, which is center line to center line, this distance is A3. And this distance, center line to center line, is A4. And some of you may ask me, these distances do not represent the physical robot because physical links have some thicknesses. But in the kinematic diagram, the purpose is to find out the mathematical relationship between the joint variables. In this case, the joint variables are θ1 and θ2 and the end effector position. So this is the first joint variable, which is θ1. You have the second joint variable, which is θ2. So idea is we want to find out the relationship between the end effector position and the joint variable θ1 and θ2. Now please note, A1, A2, A3 and A4, these are fixed. They are not changing. The only things that are changing in this figure are θ1 and θ2. And we have to solve the forward kinematics problem, which means given the values of θ1 and θ2, what are the values of xp, yp, and zp? Where xp, yp, and zp are the end effector positions. xp, yp, and zp. These are end effector positions. Clearly, we need to specify the reference xp, yp, zp with respect to what? So I'm going to say this is my coordinate frame. So this is going to be my 0 coordinate frame. So with respect to the base frame, I want to find out what is xp, yp, and zp given the values of θ1 and θ2. Everyone understood this? This is going to be the forward kinematics problem. First and foremost, whenever you see a physical robot, no matter how that physical robot looks like, in this case, this robot I showed you in a fully extended position. But this robot could very well be in folded position. First thing, what you need to do is you need to draw the kinematic diagram. The kinematic diagram is the diagram of the robot in the fully extended position when the joint angles are 0. Kinematic diagram is the diagram of the fully extended robot when the joint angles are 0. So what I'm going to do is, let's identify the joints. Can someone tell me how many joints does this robot have? 2 joints. Are they rotary or prismatic? Are they revolute or prismatic? Both of them are revolute or rotary joints. So what I'm going to do is I'm going to draw kinematic diagram. This kinematic diagram is going to look like this. The revolute joint is represented as the cylinder. Prismatic joint is represented as a brick. So revolute joint is represented as the cylinder. So I have the first revolute joint. Then this revolute joint is connected to the second revolute joint. So this revolute joint is connected to second revolute joint, and the second revolute joint is connected to the end effector. So This is the first revolute joint, R. This is the second revolute joint, and this is the end effector. You agree with me? This is the simple kinematic representation of the physical robot. Let's identify the dimensions. This dimension is A1. This dimension is A2. This dimension is A3. This dimension is A4. You agree with me? So this dimension, look at the robot, is A1. This dimension is A2. This dimension is A3. And that dimension is A4. Now, the first revolute joint has the rotation θ1. The second revolute joint has the rotation θ2. So this revolute joint has the rotation θ1. That revolute joint has the rotation θ2. So this represents the motor M1. This represents the motor M2. Everyone understood this? So we are going to stop here for 15 minutes. So one thing I want you to understand is we have a three-dimensional robot. So the kinematic diagram that we have drawn, this is called as the kinematic diagram. Kinematic diagram represents a geometric representation of the physical robot. So clearly the kinematic diagram doesn't look like the physical robot, but it captures all the links, all the joints and major dimensions. Now, first thing we have to do is when we have a kinematic diagram, we have to assign the coordinate system. Assigning coordinate system is a very, very important activity. And there are some rules that you have to follow. Rule number 1. Can you notice that there are two joints? One first revolute joint and the second revolute joint. So the first rule is the z-axis goes through joint. So in other words, what you have is you are going to have this first axis. I'm going to call this axis Z0. This is going to go to the first revolute joint. I'm going to call this second axis, which is Z1. This is going to go to the second revolute joint. End effector does not have a joint. So you are welcome to draw Z-axis wherever you want. But just to be consistent, I'm going to have Z0, Z1, and I'm going to draw Z2 over here. So these are the Z-axis. Everyone agreed? Next rule is now I need to assign x-axis and y-axis. I need to assign x-axis and y-axis. So xn should be perpendicular to Zn minus 1 and intersect Zn minus 1. This is the most important rule. Now, what does this mean? So the first revolute joint has its axis Z0. There is no other joint before that Z0. There is no other axis before Z0. So you can assume X0 in this direction. So I'm going to say X0 in this direction. X0 in this direction. You can also assume X0 in this direction. That's totally fine. Why this X0 direction does not matter? Because there is no Z minus 1. You agree with me? Xn means X0 should be perpendicular to Z minus 1 and intersect Z minus 1. Everyone understood that? So X0 does not have any Z minus 1, so we don't have to worry about it. Now, if you go up, you are going to have X1. Now, please understand, this is extremely important. You have two choices for X1. Your X1 could be like this, or X1 could be like this. Do you agree with me? X1 could be like this, or X1 could be like this. And some of you may ask me, can X1 be in this direction? Yes, X1 can be in the opposite direction. Can X1 be in this direction? Yes. Now, in other words, you have four possible choices for X1. Now, please understand, I want you to look at this. This X1 or this X1 is not intersecting Z0. Why? Can you see that there is this A2 distance between this Z0 and this X1? So X1, if you were to draw X1 here, or if you were to draw X1 here, it will not intersect Z0. Do you agree with me that they are kind of parallel? So X1 cannot intersect. So this is not the right configuration. Everyone understood this? Please understand, X1 needs to intersect cross Z0, and this X1 does not cross Z0. So this X1 crosses, this X1 crosses. Now, since I have X0 in this direction, I'm going to say, let's assume this as X1. So I'm going to assume this X1. You agree with me? This is X1. Why this is X1? Because please note, this X1, if I extend, it intersects with Z0. When you have X1, X1 intersects Z0. And now I need to add X2. X2 should intersect Z1. So again, I have choices. I can say that X2 could be here or X2 could be here. So my X2 could be in this direction or X2 could be in this direction. Please understand, if I assume X2 in this direction, it will be parallel to Z1. You agree with me? Because there is this offset of A4 between X2 and Z1. So the only viable direction is this direction. X2. Everyone understood this? Everyone understood how I found X. So X0 can be anywhere because there is no other axis before this. This X1 needs to intersect with Z0. So it has to be here. That X2 needs to intersect with Z1. So it needs to be here. So I've drawn X0, Z0, X1, Z1, X2, Z2. Now I will complete this triad by the right hand coordinate system. Check this out. Thumb is X. My first finger is Y. My middle finger is Z. Now I have X naught here and I have Z naught here. So X naught, Z naught. You agree with me? My Y naught needs to go inside the board. X, Y, Z. I have X and Z. So my Y naught needs to go inside. So X naught, Z naught. And this goes Y naught. Everyone understood how I complete the first triad? Now help me complete the second triad. I have X1, I have Z1, X1, Y1, Z1. So can you see that my Y1 is also going in? X2, Y2, Z2. So can you see my Y2 is also going in the board? So I have X1, Y1, X2, Y2, X and Z1, Z2. So my coordinate system, my frames are set up. Any questions about the frame? Now, the most important thing that you need to observe that the joint rotation is about Z-axis. And it's done because for a purpose. Because remember, our rotation matrix is about Z-axis. In other words, this frame and this frame, they are associated with the rotation matrix that we derive. Why? Because look, this theta 1, curl your fingers in the direction of theta 1. Can you see theta 1 is in the positive Z direction? Curl your fingers in the direction of theta 2. Can you see that is in positive Z direction? Which means all these rotations are about Z axis. That means the only rotation matrix that we will need to solve this entire forward kinematics is cosine theta minus sine theta, sine theta, cosine theta. That is the rotation matrix that we derived. Everyone understood this? So that's the only matrix that you will ever need. Okay. Now the question comes is how do we do this? And for this first problem, I'm going to go very slow. So my suggestion to you is when I'm deriving the rotation matrices, when I'm deriving the homogeneous transformation, please pay attention on the board. And then I will give you enough time to copy it down. But for this first problem, I'm going to derive rotation matrices and then I'm going to derive homogeneous transformation. Once you derive the homogeneous transformations correctly, your forward kinematics problem is done. Your forward velocity problem is done. Inverse kinematics problem is done. And even inverse velocity problem is done. So I want you to pay attention how do we derive rotation matrices. So first rotation matrix is called 0R1. So the rotation matrix, this is old frame. R stands for rotation matrix. And new frame. So you have, so 0 R1. So this is the old frame. This is the new frame. And please note, since the rotation is about Z naught, the rotation matrix is going to look like cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Do you agree with me? Now here is another important problem. What's going to happen is when you solve a robotics problem, you are going to deal with the frames that are not aligned. What do I mean by not aligned? So whenever you find a rotation matrix, every rotation matrix must be multiplied by the projection matrix. Every rotation matrix must be multiplied by the projection matrix. What is this projection matrix? Projection matrix is similar to the previous projection matrix that we found out. So projection off, projection on. So what is my new frame? My new frame is x1, y1, z1. What is my old frame? x0, y0, z0. Do you agree with me? So once again, I will write this down. Projection off, projection on. Now I want you to pay close attention to the figure that I have on the top. Can everyone locate where is x1, where is y1, and where is z1? Can you see x1 is in the horizontal direction, z1 is in vertical direction, and y1 is perpendicular to z1 and x1. Do you agree with me? Look at x0. X0 in the horizontal direction, z0 is in the vertical direction, and y0 is in perpendicular to z0 and x0. Everyone understood this? Can you see that both these coordinate frames are aligned? They are in the same direction. So what I want you to do is, what is the projection of x1 onto x0? Projection of x1 onto x0. Can you see x1 and x0? They are in same direction, which means this would be 1. What is the projection of y1 onto x0? They are perpendicular. So y1 has no relation whatsoever with x0. So 0. z1 has no relation whatsoever with x0. Then go to projection of x1. Can someone tell me what is the projection of x1 onto y0? x1 onto y0? 0. What is the projection of y1 onto y0? 1. Why? Because y1 is aligned with y0. Always remember, projection off, projection on. New frame, old frame, new, old, off, on. Remember this. We did the exact same thing when we derived the rotation matrix. Remember? Same thing. So this will be 0, 1, 0. You agree with me? Projection of x1 onto z0, 0. Correct? X1 has no relation whatsoever with z0. Projection of y1 onto z0, 0. Projection of z1 onto z0, 1. Everyone understood this? Now I want to talk about this case. I actually made a smart move. Think about it. And I want you to think about this case. Do you agree with me? When we decided the direction of x1, I had a choice. X1 could go towards right or X1 could go towards left. But I deliberately chose X1 towards right. Why? Because when I chose X1 towards right, it aligned with X0. And that's why I have positive 1. You see this? If I would have selected X1 in the opposite direction, this would have been negative. Everyone understood this? So in this particular problem, we could use some judgment and minimize our work. But if you have some complicated problems, wherein maybe you have links which are at an angle or configuration of the robot is complicated, there you may not be able to avoid these complications. And you may get, not saying you will, you may get negative signs. Everyone understood this? Now, this rotation matrix, which is going to be constant throughout robotics 1, needs to be multiplied with this matrix. You see that this matrix is an identity matrix. Whenever you multiply identity matrix with any matrix, you get the same matrix. So the product of these two is going to be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Do you agree with me? Now, I'm drawing this for a reason, okay? So now, what I did, I have this rotation matrix. I appended rotation matrix with bunch of zeros because I want to build this matrix, which is called as the homogeneous transformation 0H1. And how do I construct the homogeneous transformation? Homogeneous transformation is constructed by taking the rotation matrix and adding bunch of zeros at the end and adding the 1 at 4th row, 4th column. Homogeneous transformation is a 4 by 4 matrix. Homogeneous transformation is a 4 by 4 matrix. And I'm going to write this homogeneous transformation. So everyone should look at the board. Now, homogeneous transformation tells me the rotational relationship between the frames and the translational relationship between the frames. So homogeneous transformation, this homogeneous transformation is the relationship between the old frame and the new frame. Old frame and the new frame. I captured the rotation between the old frame and the new frame. I captured the rotation between the old frame and new frame. Now I want to capture the translation between the old frame and the new frame. Now please understand, this rotation matrix is appended by these 3 additional rows. So this row, and then this row. So what I have is I have this row here. I have this row here and I have this row. So I have to fill in these rows. These rows represent the translational information between the new frame and the old frame in the old frame. Once again, I'll write this down and I will explain. So the first So first row, fourth column tells you the translation of x2, translation of new frame from old frame in x old. Now, what does this mean? Now, please try to understand. This is my old frame. Do you agree with me? This is my 0th frame. This is my first frame. I want to find out what is the distance between the 0th frame and the first frame. So, translation of the new frame, translation of frame 1 with respect to frame 0 in the coordinate frame x0, y0, z0. So translation of new frame x old in the old coordinate frame. So now can you see that new frame is distance a3 in the x0 direction? Do you agree with me? It is. So what I mean by that, if you stand here and travel a3 distance in the x0 direction, you will get to frame 2 of frame 1. Do you agree with me? Stand here, travel a3 distance in the x0 direction, you get to frame 1. So that distance is plus a3. You agree with me? Now here's the problem. That distance should be valid for all the values of theta. Right now, what I have shown you is I have shown you the configuration when theta 1 is 0. But imagine if theta 1 is 30 degrees, theta 1 is 40 degrees. You agree with me? Then the relative distance between the frame 0 and frame 1 is going to be different. So how would I find that out? So whatever expression I write in this row and column here, it should be valid for all the values of theta. And I want you to do a thought experiment. I want you to look from top. I want you to look from top. Do you agree with me? Right now, my theta is 0. So I'm seeing like this. This is my A3. So I see the distance between the 0th frame and the first frame is A3. But as my theta value changes, remember we are talking about positive theta. As my theta value changes, you agree with me, this distance is going to be A3 cosine theta 1. What I want you to do is, I want you to look from top. And when you look from top, we are going to have 0th frame, first frame. When theta is equal to 0, you see A3. But as theta changes, and changes in this direction, why in this direction? Positive rotation. Our rotation is positive. This, the cosine component will come here. So here, it would be A3 cosine theta 1. Do you agree with me? So this is going to be A3. Sorry, this is A2. A2. My bad. A2 is this. This is A2. So this is A2. A2. This distance is A2. So A2 cosine theta 1. Similarly, here it will be A2 sine theta 1. Right? And what would be here? It would be A1. Because no matter whatever is the value of theta 1, that distance A1 is not changing. So here it would be A1. Do you agree with me? So translation of new frame from the old frame in X old. Similarly, translation of new frame from old frame in Y old. And translation of new frame with old frame in Z old. Everyone understood this? I would explain this once again. This is the most important matrix, homogeneous transformation. If your homogeneous transformation is wrong, your forward kinematics problem will be wrong, inverse kinematics problem will be wrong, velocity problem would be wrong, acceleration would be wrong, force problem would be wrong. So it's extremely important that you get this homogeneous transformation right. And how do you get homogeneous transformation right? You get the rotation transformation and you append the translational information from the new frame, the old frame, in the coordinate of the old frame. So this tells me A2 cosine theta 1, A2 sin theta 1, and this is A1. Everyone understood this? Okay, you can copy this down. If you have any questions, you can ask me. And I'm gonna go, and if you already have copied this down, next natural step, and I'm gonna carry that out, is find first the rotation transformation from 1 to 2. Can you see that we went from 0 to 1? Now we have to go from 1 to 2 because our end effector is at frame 2. You agree with me? So we have to go to the end effector. So 1 to 2. Yeah.
Equation is negative, what will be the changes of happen? And second question is, can you explain how A to sin theta?
Yeah. So what I want you to do is, I want you to look from top. And when you look from top, this is what you're gonna see. You are gonna see X naught. You are gonna see Y naught. You agree with me? And then what you're gonna see is you are gonna see this A3, A2. This is A2. When theta is 0. Now, as theta changes, if this theta changes to theta 1, you agree with me? This A2, you have to see A2 cosine theta 1. And then this would be A2 sine theta 1. So you are looking from top. And you will always write that distance in the old coordinate frame. Even though you are trying to find out the distance between the frame 0 and frame 1, that distance need to be expressed in the coordinate frame of x0, y0, and z0. Everyone understood this?
So.
They're 1. That always will stay 1. So this is how the homogeneous transformation matrix is defined. Why do we need homogeneous transformation matrix? Because remember, we have a rotation matrix, we have information about the translation. At the end, we are going to start multiplying matrices. So for the matrix multiplication, we need to have square matrices. So a homogeneous transformation matrix is defined with the rotation matrix in the first 3 by 3 matrix. The last row will be 0, 0, 0, 1, and the last column would be translation. That is how the homogeneous transformation matrix is defined. Everyone understood this? Now what I'm gonna do is, I'm gonna derive the rotation matrix. And before I derive the rotation matrix, now please notice, I'm gonna derive the rotation matrix, which is 1 R2. Rotation matrix 1 R2. You agree with me that rotation matrix also represents rotation about Z. You agree with me?
Yes.
The only difference is now that rotation instead of theta 1 is theta 2. So the rotation matrix that we derive will remain unchanged. The rotation matrix that we derived will remain unchanged. Similar to this rotation matrix, what I need to do is first write the rotation matrix, multiply that by the projection matrix. But remember, now our frames are different. Initially here, my new frame was x1. My old frame was x0, y1, y0, z1, z0. Now, since I'm going from 1 R2, 1 R2, my old frame is going to be x1, y1, z1, and my new frame is going to be x2, y2, and z2. You agree with me? Other than that, everything will remain the same. Now, I will derive this, but what I want you to do is, I want you to focus on the frame x1, y1, z1, x2, y2, z2, x1, y1, z1, x2, y2, z2. Do you agree with me? Rotation is about z. So the rotation matrix is not going to be different. Only difference would be, it would be cosine theta 2 minus sine theta 2, 0. Sine theta 2 cosine theta 2, 0, 0, 0, 1. Do you agree with me? But again, it needs to be multiplied with the projection matrix. But now the projection matrix will be x2, y2, z2, and x1, y1, z1. Do you agree with me? However, since we decided when we were solving the problem, note x2, y2, z2 aligns with x1, y1, z1, which means the projection matrix will be unity. Everyone understood this? If I would have assumed my axis in any other direction, you will not get the wrong answer. But you need to make sure that your signs in the projection matrix are appropriate. Once again, I repeat, and I'm explaining this because when I start writing the rotation matrix, that figure may not be visible. So I want you to understand, I had to repeat the exact same process. But now, instead of 0 R1, it would be 1 R2. So this becomes cosine theta 2, sine theta 2, minus sine theta 2, cosine theta 2, 0, 0, 1. And here it's going to be x2, y2, z2, x1, y1, z1. Since x2, y2, z2 is aligned with x1, y1, z1, my projection matrix will remain identical. Everyone understood this? We are going to solve quite a few problems where you will see that this projection matrix will flip sign and all that stuff. I want you to understand, for the very first problem, it shows the same trend. So I'm gonna do 1R2. 1R2 will have the rotation matrix cosine theta 2, so minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And why this same rotation matrix? Because the rotation is about z. This rotation is about z. This rotation is about z. That's why the same rotation matrix. Rotation matrix doesn't stay alone. Rotation matrix must be multiplied by the projection matrix. Projection of, projection on, projection of x2, y2, z2. Why? This is the new frame, new. And projection of x1, y1, z1. So projection of x2, and I'm going to show you here. Can you see x2 is aligned with x1? So the projection is going to be 1. Y1, y2 is aligned with y1 and z2 is aligned with z1. So this projection is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And some of you may say that this is trivial, but till you get very comfortable, please write the rotation matrices completely, projection matrices completely, perform the multiplication, and as you solve more and more problems, you can just look at the problem and write the rotation matrix. But for at least for first few problems, follow these steps. Now the next thing what we need to do is, we need to derive the homogeneous transformation. To derive the homogeneous transformation, we start with 1H2. And in 1H2, first I'm going to rewrite this matrix. Cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Do you agree with me? Then I'm gonna add this guy, and this remains every time you do it, it remains the same. 0, 0, 0, and you're gonna have 1. Now, before I will give you what is over here, but I want you to take a guess. So what is here? This is the distance of frame 2 with respect to frame 1 in x1. Distance of frame 2 in with respect to frame 1 in y1. Why y1? Because that is the old frame. Why x1? That is the old frame. Similarly, distance in z1. Do you agree with me? And just take a guess. Tell me, what would this be? A4 cosine theta 2. Everyone understood this? Because now you will do the same activity. Look from top. Now you will notice that when you see you have A4, but A4 is when theta 2 is equal to 0. As again, positive. As soon as that A4 changes, as soon as A4 rotates, you are going to have A4 cosine theta A4 cosine theta 2, A4 sine theta 2, and A3. Everyone understood this? Okay, guys, you did all the hard work. Now, how do we solve forward kinematics problem? Where are we? We are at 0 position. We are at 0. Where do you want to go? To frame 2. So 0 R1 multiplied by 1 R2. Can you see 1 gets cancelled, gives you 0 R2. Now 0 H1 multiplied by 1 H2 gives you 0 H2. You agree with me? So check this out. This is the first rotation matrix. This is the rotation matrix. First rotation with respect to 0. Second rotation with respect to 1. When you multiply these two, this first frame cancels out of the equation and you get rotation of the second frame with respect to 0. Here, the first homogeneous transformation multiplied by the second homogeneous transformation gives you the final product of homogeneous transformation. Everyone understood this? Any questions? Now, here comes the tricky part. Tricky part is 0, 0 H1. So if I want to find 0 H2, I need to be multiplying 0 H1 multiplied by 1 H2. And so what we have to do is, we have to multiply two 4x4 matrices. The way to do this is, program these matrices inside the MATLAB and ask MATLAB to give you the answer. But in the first class, I'm gonna multiply these by hand so that everyone knows how the matrices are multiplied. And now I'm gonna write 0 H1 and I'm gonna write it, make sure that I write it correctly. Cosine theta 1 minus sine theta 1, 0 sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0, and this is A2 cosine theta 1, A2 sine theta 1, this is A1, this is 1. You agree with me? Multiplied by second homogeneous transformation, cosine theta 2 minus sine theta 2, 0 sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0. This is going to be A3, right? A3 or A4? A4. A4 cosine theta 2, A4 sine theta 2, and then this will be A3, right? A3 and 1. Now I'm gonna get this long multiplication. So make sure that I don't make mistakes, because it's quite possible I may not be doing it correctly. First row, first column. So I'm gonna take this first row and multiply with first column. So check this out. This will be cosine theta 1, cosine theta 2, first row, plus minus first sine theta 1, sine theta 2. So first row, first column. Then first row, second column. First row, second column is cosine theta 1 minus sine theta 2. Then minus sine theta 1 cosine theta 2. Then first row, third column. So can you see here I get 1. And first row, fourth column. So first row, so this is going to be A4. I need to use more space. So it's going to be A4. First A4 cosine theta 2, A4 cosine theta 2, cosine theta 1, then minus A4 sine theta 1, 2 sine theta 1. Then I'm gonna have 0, and then I'm gonna have the last term here is A2 cosine theta 1. Now let's do the second one. Second one becomes sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2, then minus sine theta 2 sine theta 1 plus cosine theta 1 cosine theta 2. I get 0, and then here I'm gonna get A4 cosine theta 2 sine theta 1, and make sure I'm not making any mistake. Then plus A4 sine theta 2 cosine theta 1 plus A2 sine theta 1. Third row, first row, third column. First row, third column, did I make a mistake? A4 cosine theta 2 cosine theta 1, A4 sine theta 2 sine theta 1 plus A2 cosine theta 1. No, that's correct. Oh. A2 cosine. Where did I? So, okay, let me understand. Is this wrong? No. This is wrong? This one?
No,
The one before
the
what?
third column,
Fourth column, third column.
one, that one there.
Oh, yeah. That should be one.
1, right? It should be 0. Okay, let me see. Yeah, that's correct. This should be 0. Yeah, this should be 0. That's correct. Okay, next, when I do, there will be 0 here. There will be 0 here. There will be 1 here. That's correct. So this is wrong. And the last thing here is the third row, third column, everything 0. Here comes A1 plus A3. 0, 0, 0, 1. Now this, I can partition it like this. This, I can partition it like this. Now, what I want you to do is, I want you to tell me if you see Maybe any interesting patterns here? Do you see any interesting patterns here? Can you see the first term is cosine theta 2, cosine theta 1, theta 2, sine theta 1, theta 2. So what is this identity? Do you agree with me that this identity looks like cosine theta 1 plus theta 2? Do you agree with me? If you expand cosine theta 1 plus 2, it becomes cosine theta 1, cosine theta 2, minus sine theta 1, minus sine theta 2. Remember expansion of cosine? Okay. What happens? What is here? What is this guy? Sine theta 1, cosine theta 2, cosine theta 1, sine theta 2. Remember this identity look like sine theta 1 plus theta 2. You agree with me? Now tell me, what is this guy? Minus sine theta 1 plus theta 2. And this is cosine theta 1 plus theta 2. Do you agree with me? Do you see any pattern emerging? Okay, good. Here comes 0. Here comes 0, 0, 0, 1. This is 0, 0, 0. Now, since I already gave you hint, what I'm going to do is, I'm going to take A4 common outside. So can you see, once I take A4 common outside, I have cosine theta 2, cosine theta 1, minus sine theta 2, sine theta 1, which is nothing but A4 cosine theta 1 plus theta 2 plus A2 cosine theta 1. Do you agree with me? Here, if I take A4 common outside, what do I get? Sine theta 1 plus theta 2 plus A2 sine theta 1. And I have A1 plus A3. Okay, we have solved the forward kinematics problem. Because what is this matrix? This is 0, R2. This matrix is 0, R2. This guy. And now if you notice, what this is telling me, that rotation of frame 2 with respect to frame 0 is nothing but theta 1 plus theta 2. And that makes perfect sense. Do you agree with me? If you look from top, now what you have is, you have the first joint and then second rotation. So if you look at the overall rotation is theta 1 plus theta 2. So this is your arm, this is your robot. So the first rotation is theta 1, second rotation is theta 2. First rotation is theta 1, second rotation is theta 2. It means the total rotation is theta 1 plus theta 2. That's what this guy is telling me. And here, I'm finding out the distance between the frame 0 and frame 2. And I will show it to you. So this is your robot. This is your first link. And then this robot, there is this second link. Now here, this is A4. This is A2. Now please note, This is your theta 1. This is your theta 2. And your initial frame is this. So this is your initial frame. So now if you look at this angle it's same as theta 1. So this is your x-axis, this is x naught, this is your y naught. Why x naught and y naught? Because we want to solve the forward kinematics problem, the zeroth frame. All the translations should be with respect to zeroth frame. This rotation that we have found out is with respect to z naught. It's not with respect to z1, it's not with respect to z2, it's with respect to z naught. Okay, so theta 1 plus theta 2, the overall rotation. Can you see if you look from top? This is your x, this is your y, your z is coming out. X, y, and z. So I'm showing you from top view. So do you agree with me? This distance is a4 cosine theta 1. And this distance, can you see that this distance is a2 cosine theta 1 plus theta 2. That means your end effector from your zeroth frame in the horizontal direction is a4 cosine theta 1. Look at the last term. No, this, yeah, a2. This is a2. A2. This is a2 and this is a4. a2 cosine theta 2 and a4 cosine theta 1. If you look at the horizontal, since you looked at the horizontal one, let's look at the vertical one. This is a2 sine theta 1 and this guy is a4 sine theta 1 plus theta 2. And your z, x, y, z is coming out. So if you look at the overall rotation about z, which is nothing but theta 1 plus theta 2, that's what the rotation matrix is telling you. And since we are looking at the two-dimensional figure, that a1 plus a3 doesn't come in the picture, but it's like elevated. So do you agree with me that whatever answer that we get with forward kinematics using the homogeneous transformation, we can verify the forward kinematics using a graphical approach. So whenever you solve the forward kinematics, and maybe you have 2 links or you have 3 links, it might be just worth your while to sketch and ensure that the answers that you get from the calculations correspond with the answers that you get from the geometry. Everyone understood this? It's really important. Any question about the problem that we have solved? Any question about the problem that we have solved? Any question? Now comes the quiz. So this quiz is close computer, close phone. So I don't want to see any phones or computers on the desk. Only notebooks, everything should go in your backpack. Hey, Mohammed, you will see around and make sure that nobody's cheating. If they are cheating, don't say anything, just take a picture. they have consented to photographs already. Last chance. Any questions? Oh, these notes will be posted on Canvas. Don't do. Okay. Everyone's phone and laptop. Okay. So here is the quiz question. So here is how you are going to solve it. I'm going to give you the quiz question. Then I would give you some hints on how to solve that quiz question. And then you'll work out the quiz problem in your notebook. After that, you will take the picture, and some of you, if you have PDF creator or something like that, you can create a PDF. And at 8:45, I would say stop. At that time, you will take the picture and upload it onto Canvas. So everyone understood? So we will work out the problem for next 15 minutes. Then, yeah.
I wrote that. That's why I can.
Okay, no problem. Take a picture and email it to Mohammed. Anyone else has any other question? Anyone planning on dropping the class? Okay, so question. You guys think I did a good job? Okay, then I'm gonna give you a hard question. Okay. So solve forward kinematics problem. Yeah, you can write the question. And Mohammed, you also work out. So I would check your solution and you will check everyone's solution. She's so happy that there is only one more student to suffer. TA is also suffering with me. So I don't expect you to solve this. This is a planar problem. This is not a three-dimensional problem. This is a planar problem. This is not a three-dimensional problem. So I don't expect you to construct a kinematic diagram and all that type of stuff. But here is the problem. What you have is you have a cylindrical robot. This robot has the prismatic joint. So which means the extension of the piston is given as B. This distance A is constant. So this distance A is constant. So you have D that is changing. And this piston is able to rotate by angle theta. This piston is able to rotate by angle theta. Actually, I can make it even easier. So I say that this extension is D. So this extension is D. And this rotation is theta. So there are two joint variables. D is the extension of piston, or cylinder. And this is the end effector. Here is the end effector. And theta is the rotation. And you have to find out position of the end effector, xp and yp. xp and yp as function of d and theta, as a function of d and theta. And you have to tell me the orientation of end effector with respect to z0. And I will tell you this is x0, this is y0, and you have the z0 coming down.